Hello everyone, I'm Seyed Mohammadjavad Talebi from UC Irvine. This work was a collaboration between researchers from UC Irvine and UC Riverside. I'm talking about CHARM, facilitating dynamic analysis of device drivers of mobile systems. First, let's see what is the problem that CHARM tries to solve. Today we use our mobile systems everywhere, from sharing our family photos in social media app to paying our bill in our banking application. The security of mobile system is very important. These mobile systems are diverse. There are thousands of distinct Android devices in the market made by different manufacturers. And this market is very competitive. Different vendors try to attract their customers by adding new features. One might add a new high-end camera, while another one using a new fingerprint modules. These new features means new hardware, and new hardware needs more new device drivers to be managed. So there are a lot of device drivers out there. The time to market for device drivers is short, and they are vulnerable to errors. And a study shows that 85% of bugs found in Android kernels were due to errors in device drivers. So we need efficient ways to analyze device drivers and find bugs and vulnerabilities in them. It has been shown that dynamic analysis is very useful for find vulnerabilities in software. There are many techniques like fuzzing, interactive debugging, record and replay, selective symbolic execution, and dynamic taint analysis, which have been used for find vulnerabilities and analyze them. Many of existing tools, many existing dynamic analysis tools use virtual machines. For example, two fuzzers, KFL and dig tools that were introduced in last year using security use virtual machines to work. And if you want to use GDB for the kernel, you need a virtualization environment. The QEMU, with help of virtualization, provides some record and replay. S2E also used virtualization, and a whole system a dynamic taint analysis called decaf also used virtual machines. But the problem is that applying these tools to mobile systems, especially device drivers of mobile system, is hard. Why? Because one reason is hardware-assisted virtual machines are not supported in many commodity mobile systems, and software-only VMs leave you with a very poor performance. So let's see how we can tackle this problem and solve it. Our idea is to run the device drivers of a mobile system in a different physical machine. For example, a powerful x86 server. The problem with that is that the execution of device driver is tightly coupled with its underlying device. And without access to its I/O, the driver execution will fail, and we cannot analyze that. Our idea to solve this problem is forward low-level I/O operations and use an actual mobile device to serve for these I/O operations. Let's see how we design the system to implement this idea. First, before going to implementation of our system, let's have a closer look to device driver of mobile system. The driver is running within the kernel of mobile system and interacts with the device in several ways. One of them is memory mapped register read writes to control registers of a device. If an event happens and the device wants to notify the driver, it will use interrupt. In the system, there also are some shared resources like clock, power management, GPIO, and pin controller that the driver needs to manage for its device. Linux kernel provide APIs for sharing these resources and accessing shared modules. For example, the device driver can call functions to this API to adjust the clock frequency or change the voltage of a regulator. Having this knowledge of device driver, let's see how we can move the device driver to the workstation kernel and run it in a virtual machine. First, we need to disable the device driver in the mobile system, since we don't want two device driver managing one device. Then we can move the code and build it within a kernel of the virtual machine. As I mentioned before, the driver needs to manage the shared module, shared resources using shared module by calling kernel API. But we cannot move the shared modules to the workstation kernel, since if we disable these modules in the mobile system will not boot and we cannot use it for remote I/O accesses. So we decided to keep the shared modules in the mobile system and access them remotely. I will discuss it later in the slides. So let's see how we handle remote I/O operations. For this purpose, we use two stubs, one in the workstation hypervisor and one in the mobile system kernel. And we connected them using a USB channel. I should mention here that a device driver and its underlying hardware interactions is very time sensitive. And we could not use a normal USB channel like famous ADB, because due to many layers of indirection, the latency of this channel is high and it will result in many timeouts. So we built our own USB channel which connects the hypervisor of the workstation to the kernel of mobile system directly. And we reduced the latency and avoided timeouts. Having this low latency USB channel, we can implement all the interfaces between the driver and device remotely. First interface is remote register read and writes. We know the physical addresses range for each device, and we can track those addresses in the hypervisor of our workstation. And if any register access happened on those addresses, we can forward it to the mobile system using our stub. Since we disabled the device driver in the mobile system, we can capture all the interrupts that the device issued inside our stub in the mobile system, and we can forward them to our workstation and inject them to the kernel of virtual machine. And when the device driver wants to manage the shared resources, we build a remote procedure call on top of the Linux API for sharing, managing the shared resources. So we can manage those resources remotely from our workstation. By having these three interfaces, the device driver will successfully initialize and work inside the virtual machine, and we can run different dynamic analysis on top of that. Let's see how well this system works. To show the generality of our system, we ported 4 major device drivers, naming camera, audio, GPU, and IMU sensors drivers to our system. And we ported these drivers from different phones, 3 different phones from 3 different manufacturers. For this purpose, we ported thousands lines of code. One important metric for our system is the time it takes to port a new driver to our system. For this purpose, after finishing the implementation of our system, we asked another author of our paper to port new driver to our system, and we measured the time it takes to port a new driver. You can see that porting GPU driver, which is a huge driver to our system, took 7 days, and porting IMU sensors to our system took 2 days. I should mention that this author has good knowledge of kernel programming and device drivers. Another point that it's worth mentioning here is that most of the process of porting a new device driver to the system is mechanical and constant, and we plan to write an automatic program to port a new driver to our system in future. Having these drivers in our system, we can run several dynamic analysis tools and techniques in our system. The first one is fuzzing. Fuzzing, as you may know, is testing the program by feeding random inputs to it to see whether the program crashes or anything happened to it or not. Our system facilitates fuzzing in several ways. For example, KFL and the tool that I mentioned before use virtualization. And because we run the device driver within an x86 machine, we have Intel VTX, which facilitates virtualization. Also, PT trace can provide more feedback information for the fuzzers. If you want to find more bugs in the kernel, especially non-crashing bugs, there are some kernel sanitizers which are helpful. For example, KSON and KMSON helps to find memory bugs like out-of-order, out-of-bound accesses. And KTSON is useful for find data races bug. Because mobile systems usually use older versions of kernel, these sanitizers are not available for all the mobile systems. But using our system, we can have these mobile sanitizers, kernel sanitizers, and find non-crashing bugs. Another thing is that to fuzzing, you need to have the output of the program and you need a reliable console access. This task is hard for many mobile devices because you might need a specialized hardware, or in some cases you need engineering effort as soldering new devices to your system, which in our system is not necessary because we use the normal USB channel. To test the fuzzing performance, we experimented two scenarios. In scenario 1, we run the fuzzer on a phone, and on scenario 2, we execute the fuzzer on an x86 server using our system. One good metric to measure the performance of the fuzzer is number of the fuzzer inputs you can run within a given time. You can see that based on this metric, our system have a slightly better performance than native execution of the fuzzer on the phone. It might seem surprising first, but we should notice that in the fuzzing application, because the inputs to the device drivers are random, they're not causing many low-level I/O operations. And because we're running on an x86 machine, we have a higher performance cores to execute, which can compensate for the I/O forwarding cost. So by this, we have a slightly better performance on fuzzing application. After we fuzzed our drivers using our system, we could find 25 bugs. 14 of them were new bugs, which we reported, most of them to driver developers. 2 of these bugs found by kernel sanitizers, which were not available on that phone. And the good news is that although we fuzz the system using a different machine, which has a different architecture, and we change the timing of the device driver by forwarding the I/O, we could verify all of these 25 bugs on the phone, and none of them were false positives. The next dynamic analysis that we tested on our system is record and replay. Record and replay, especially for mobile device drivers, is challenging and without our system. But because in our system, all of the interactions of the device and the driver are going through a well-defined interfaces, which all of them goes through our stub in the workstation hypervisor, we can record all of these interactions while we do the record in some logs. And when we're replaying the virtual machine, we can use our log to replay all of these interactions. The good news here is that you don't even need that specific mobile system when you're doing replaying. For example, consider this scenario that you're fuzzing a device driver and you find a bug while you were recording. You can send the log to any expert in any in a different locations, and he can analyze that bug for you without accessing to that specific mobile system. To measure the performance of record and replay in our system, we measured the very I/O intensive task, which is camera initialization time. Because in this process there are a lot of I/O operations, we can see the time it takes to initialize the camera driver in Charm is more than that time, the same time in the phone. And when we do recording, we have a slight performance overhead. But the good news is that when we replay that same process, we have a good performance, which is even better than normal execution of the camera driver on the phone. The next dynamic analysis that we tested in our system is manual interactive debugging. Because we run the device driver, within a virtual machine, we can use the GDB. We can use the GDB on our VM and the device driver. So we can add breakpoints to the code. We can add watch points to see memory interactions, and even we can do single-step execution on the device driver. Using these capabilities, we could analyze 3 known vulnerabilities, and we also can build an arbitrary kernel code execution exploit using one of these vulnerabilities with help of GDB. Because we have GDB, we can easily see the heap object allocation and also memory layout, which helps us a lot in building this kernel exploit on top of out of bound write vulnerability. I want to compare our work with two of the most closest related work, Avatar and Surrogate, which both of them, same as our system, use I/O access forwarding in low-level I/O accesses. But the main difference is that the target. In Avatar and Surrogate, their target system is the whole closed-source embedded system firmware binary. But in our system, we want to support a part of mobile system software, which is open-source device driver. And the communication channel is different in our system too. We use the normal USB, which is available everywhere. But Avatar used the UART and JTAG, which leads to very poor performance. And Surrogate use PCI Express FPGA board, which is not available everywhere. We plan to automate the porting driver to our system in our future work. We also plan to support the DMA as another interface between the driver and the device. And in addition to many open source device drivers, which Charm already supports, we plan to support binary drivers as well. In summary, our system facilitates dynamic analysis of mobile device drivers. Charm's performance is similar for dynamic analysis like fuzzing. It's similar to the actual mobile systems. And Charm supports a broad variety of device drivers with reasonable engineering effort. Should mention that our system is open source. You can find it in this link, and using that QR code, our slides will be available in using security website. And I'm going to demo our system tomorrow at the poster and demo session. Thank you for your attention and time. I'm happy to answer your questions.
Hi. First of all, thanks for the talk. It was great. I have a short question. So I was a little bit confused when you said, as part of your motivation, that mobile system, and by mobile system, I just assume that you're targeting all the ARM-based systems on the market, don't support hardware virtualization, and therefore we don't have virtual machines which are running on ARM, basically. Have you looked at Zen? Because Zen does exactly that, and for several years now. And my question is, why didn't you just port something like KAFL to Zen?
Thank you. That's a good question. Although ARM architecture supports virtualization and we have Zen, the virtualization hardware is not supported in many mobile phones, for example. They locked it because they want to prevent rootkits to use them, and they're locked, and you cannot use for example, for a Nexus phone, you cannot have a hardware assisted virtual machine on that, although the architecture support that.
All right, but yeah, still, there are development boards where you could do basically the same. But all right, that answers my question.
Yeah.
Thanks.
Any other questions? I have one. So of all the bugs you found, how many were exploitable?
So thank you. That's a very good question. For example, most of the bugs that we find were null pointer dereferences. And these null pointer dereferences can directly be exploitable in some scenarios. And I found a study I can share you after the presentation that even the bug is not directly exploitable. There is a new project that they could build an exploit using denial of service bugs. For example, any bugs that can crash the system. They exploit something in crash handling that can result in arbitrary code execution. And if you have any bug that can crash a system, crash parts of the system that that project supports, it can lead to exploit. But and two of our bugs were out-of-bound memory accesses, which they also potentially can be exploitable, but we didn't build any exploit on top of that ourselves.
Hi, thanks for the talk. Aurélien Francillon from Euricom. My question is, if I understand well, you currently support only drivers for which you have the source code, and you do some instrumentation on the driver. What would it take to support binary drivers?
Yes. The most important part is that for supporting binary is for support for our RPC interface, we need to change some part of the code that on binary, some part of the code of the driver. The changes are small, but there are. And for supporting binary drivers, we should do binary instrumentation to change those parts of the driver. But they can be supported.
Thank you.
Yeah.
Well, let's thank our speaker.